So, hello, welcome everybody. Let's start with our lecture. Last time we talked about the question whether we can use an energy-based modeling in a more global sense. And at the very end, we ended up with these nice equations, namely the Euler-Lagrange differential equations, which tell us that physics behaves according to some sort of energy principle. That we started, and it's quite easy to quite easy to calculate the equations of motion, the state equations, if you like, if we look at this set of differential equations. So the wonderful thing is you just collect all the storages of your entire system, put them into L, so namely the kinetic energy minus the potential energy. Be aware of nonlinear elements and kinetic co-energy or the co-energy T star, and then put this into this formula, and you end up with the equations. And as you remember from OBS, it's to get the trajectories of the system, to get the dynamic solution. It's a two-step procedure. You start with this, and by solving this, you have as an intermediate step the ODEs, the ordinary differential equations, and there we are. These ODEs are usually the state space equations which you need for any kind of multivariate control you learned in other lectures, like in SRT, system dynamics and control, where we started with the state space model as a starting point and did the linearization, like Locus methods and other things. But here we are, basically like this. The wonderful thing of that is we collect all storage energies values, even if they are coupled or not. This is very important. At that point, it's quite easier to find the state space equations because you just look at all storages in your system and put them into this nice formula. On the disadvantage side, you find something that you have to know, the coupling via the non-redundant coordinates. So beware of this. Here, you don't see any kind of tilde with which I denoted the redundant coordinates. As you know, some of the storage might be coupled in an algebraic way. So the answer is, if you know a set of non-redundant coordinates of the systems, namely Q, E, J, then everything is fine. We just collect the storages, could then do the calculations, and here we have it. Well, basically, that's it. And with that, we have our equations of motion, and we already know, okay, they are governed by a energy-based principle. I want to highlight the second box here. The first box we deduced by our own, by a virtual displacement principle. The second box can be also deduced. If you remember, our virtual displacement consideration started with a nodal equation of one capacitor, if you remember that. So we started. So usually, if I click, it should move on the opposite side. We start with something like that. So we just consider this node here and distinguish between external flows or portions of external flows and internal flows, which are gluing all the network, the entire network together. We can also do the same consideration with a loop-based approach. So saying, let's have a look at the loops and do the very calculations. Then you find these considerations in the book of well set also. So if you're interested in this calculation, I want to find the second box and do these tedious calculations here. Then you will find this one, and this is somehow different, but be aware of the following thing here. And the top equation, sorry. Now we can, oops. Wow, this is not working. I thought this might be possible. So here we look at QEJ. So the accumulated effort variables. And in the second, we look at the accumulated flow variables, which means this is just a different perspective of the same system. Different perspective means in one case, you take the accumulated flow. For example, effort variables. Think of mechanical systems. The effort variable in our mechanical setting is the velocity. The velocity integrated is the position. So there it makes very much sense. So this consideration. But if you think of an electrical system, for example, the accumulated effort, so voltage integrated, is the flux. And so we are not used to doing the calculations with flux equations. Remember, so you have to know the flux variables. We are not used to that. So this is possible, but somehow not our natural way to express our equations. In contrast to that, the second equation, there we have the accumulated flow variables instead. And this means flow integrated, means in electrical systems, the flow is the current integrated gives the charge. So this makes sense. So thinking in charge values may be of interest and more interesting than flux. Well, so instead of working at the ETI, so if you're a electrical engineer and doing motor design, and you're very confident working with the above equation. So sometimes it makes sense to express your variable and your equations of motions in one set coordinate setting or the other. Obviously, but they give the same equations of motion, but looking on them on a different perspective. And this different perspective is like coordinate change. So, and you can transfer the first equation into the second by means of the so-called Legendre transformation, which you might have heard somewhere else, also in OBS, I think, and this. So you can transfer these two equations into another, and it's just a different type of perspective, and it depends what equation you use. It depends on with which set of variables you are more familiar with. That's the question. Okay. Well, I also start with this equation, this setting, which was inspired a little bit by the first lecture of Feynman, where he talked a little bit about his school days, where he learned something from his physics teacher, that the equation of motion of a point mass follows some minimization principles. And I found this also inspiring. And the interesting fact that the physics teacher told him was, well, take any equation of motion of any object in the real world, it will always behave according to the following principle. It minimizes the mean of the difference between kinetic and potential energy. And this is something which you also discovered by means of your knowledge of ODS, because you know the Euler-Lagrange differential equation of course, and then you know it's some sort of optimization principle. And if you go, well, so if you do inverse engineering more or less, then you end up with the following setting. You minimize the action value, so the difference between the kinetic minus the potential energy, and the integral over it. This is the dynamic optimization principle, and you end up with the very same equations. And this is a rigorous setting, and this is the fundamental principle. And the interesting fact is, so that nature behaves according to an optimization principle. Physical nature, pneumatics, electrics, mechanics, and so more or less everything. And it's also one of the basis of the further considerations if you want to get the fundamental justification of quantum mechanics. It starts here. Nothing for us, but because we are not dealing with quantum systems here as control engineers, even if there's a small community appearing how to do control in quantum systems. Well, the usual things we are dealing with are for huge objects, and they behave according to the traditional world. The Newton mechanics applies, and also this kind of Hamilton or even branch mechanics applies. And this is fascinating from this general position, saying, okay, general understanding, we have this thing, and to that some sort of optimization principle has to be solved. And if you remember your variation principle from the ODS lecture, you end up with the following thing, and that's exactly what Feynman does, what compare the different trajectories with each other. Due to the fact that we have an infinite number of trajectories possible, we have to get them in our hands, and the famous idea of Euler was to just vary the trajectory based on the assumption that what happens if I had the optimal trajectory, what would happen with the situation. And it's exactly this picture here. You vary it according to this fascinating principle. And physical works, then you can derive the Euler-Lagrange differential equation. And remember, ODS lecture, there we did the classical calculation, and this type of finding the first order derivative as being the necessary condition for a classical optimization problem is sometimes also denoted by this delta J as being the definition of dJ with respect to d epsilon at the point epsilon is equal to 0. It's just an abbreviation of what we use. It's called variation delta J. That does not have anything to do with the virtual displacement. Be aware of that. It does mean it's the fluctuations or deviations from the optimal value of the original trajectory. So here we see delta x is epsilon eta, and delta u is epsilon psi, and with that we get some sort of formal justification of what we learned with the virtual displacement. And it's somehow given in the following setting, and you find this in Berg's this notation. If this variation is stationary, meaning it's 0, then we find the optimal value, and we get the equations of motion. That's it. And we did it here with our principles, and I want to give you some insights for some specific systems first, and then we can develop this further. You can also say a system which does not consume any kind of energy and does not dissipate energy. So there are no sources and dissipative elements. There, obviously, the right-hand side, nothing comes in, nothing goes out. Everything stays in the system. And then the equations of motions are given by this fact: delta J has to be 0 with L equal to T star minus U. And there exists also the opposite principle, which is given here. And this solving this kind of equation means, well, we get the Euler-Lagrange differential equation. It's just a different perspective on the same problem. Okay? And so explicit notation written out, that's what the engineers are interested in. So the first one is more from the theoretical side. Right? So if we have conservative systems, this applies, and you know variations vanish. But from a practical point, we are interested in the state equations. I will show you later on. We can also deal with the equations of Euler-Lagrange directly and Hamilton also directly. There is a topic which is treated in the next chapter, where we can do, where we can work directly with this energy-based modeling perspective. But for the moment, it's sufficient to know, okay, I get the state space equation out of these equations, and they are called Euler-Lagrange relation for the second part. So it's the kind of how we do get the equations of motion. And for conservative systems, as you see, the right-hand side vanishes. That's plain. That's simple. That's what you have learned with Richard displacement also. So it's very same. Right-hand side is equal to 0. If you have sources, if you have dissipative elements, it's necessary to include them. So the deviation from 0 can only be given by the sources and the dissipation. Also something which we can bear in our mind. So also physics or say a general understanding. Changes the kind of how the variation, how much the variation does not vanish. Okay, so, and here a short glimpse on systems which do not have just holonomic constraints, but non-holonomic constraints. It's possible to include them. And if you remember, the non-holonomic constraints are split into two parts. The one which are governed by relations, so inequalities, for example, and the one which are derivative non-holonomic constraints, which are a little bit strangely defined, meaning first saying, well, these are those constraints which can't be fit in a algebraic relation. These can be treated in this Euler-Lagrange formalism very easily. So think, for example, on a non-holonomic constraint, which is the constraint which is linear. So, for example, the sum of a I times q and m dot is plus some constant. It has to be equal to 0, which is the derivative one. Remember the rolling penny problem. Then we can put them on the right-hand side and then solve the differential equations, and we get some sort of additional Lagrange multipliers. That's what happens here. But these are type of systems which we don't want to treat on our consideration. Okay. Again, as a summary here, both formulations are similar. They are linked by the Legendre transformation. Different physical quantities serve as state variables, and sometimes it's helpful to use some of the parts in the form 1, so the nodal representation, and some of the parts as the loop representation. I want to show you one example in a second. In particular, in the coupling of electrical and mechanical systems, this happens very often. And of course, there's an alternative formulation, which is the Hamilton formalism instead of using the Euler-Lagrange formalism, as you know. Sometimes it's easier to get the differential equations out of this. So it depends a little bit on your habits, how much you use the one or that one. Here, just for your convenience, the table which shows the different energies in the different domains, and then you can put it here. Now let's put everything together in a example. And I want to show you one example which is very, very interesting. I think I can tell you that yesterday I visited a company which is one of the hidden champions, which is the Physical Instruments. Just a question. Who knows the company Physical Instruments? 1, 2, 3. Not so much. close by, near Karlsruhe, and they are dealing with nano positioning. So systems which are positioning platforms in any directions and on a micrometer scale, nanometer scale, and since some years, picometer scale. So it's close to what physics allows. And well, we're working together with them in some sense, and they showed me the or we talked about different projects. It's not a problem, but one problem is, for example, positioning of platforms which are, for example, gluing together fiber optics. You know, today fiber optics is a really important topic today because we are transferring our internet values through fiber cables, and these fiber cables at some point they end. They are not infinitely lengthy. So we have some fiber, and the second fiber, and at that position you have to glue them together. This is not done manually. It's done automatically. So you send a optical signal through one fiber second, and then you try to adjust them mechanically, and then you take some source, whatever it is, to glue them together to get a optimal connection. And this positioning is in micrometer scale. And you have to rotate it, you know, by any position. You have a 6D, so all dimensions, all directions, and all positions are possible for both. So you fix one, and the second can be rotated, oriented in every position, and should position point to exactly the position of the other one. If this is not done correctly, it works. I always think that Vodafone uses bad technology because always they my internet crashes at some point, and here we are university free speech. I tell you that, but I'm not so happy with them at the moment because they are not delivering what they well say they want to deliver. But whatever it is, I think sometimes they have problems with their fiber optics and use bad material. So one task is to do this positioning, and if you know, it's really happening everywhere on the world. And this company delivers the positioning system, for example. The same applies, for example, if you do the latest generation of embedded devices, so microcontrollers, whatever, you have the same thing. Putting the structures on semiconductors is also something which happens with such a thing, and the base material, so basically the positioning system comes here from 10 kilometers north of Karlsruhe, or in the direction of Stuttgart, so to say. And well, as far as I know, they have a market share around 9% or so. So it's interesting. So almost everybody buys them for some specific areas. So, and what kind of positioning system could you use? Obviously, not a classical mechanical one, because if you have just a spindle-driven kind of mechanical device, it has friction and so, and there are some different strategies to do that. And one is using piezoelectrics, which is one with which this company became famous. But also classical traditional ones, like the following, and I really abstract the situation a little bit. It looks like this. Suppose you have some coil, and inside this coil you find a piston, and what happens? you know, from physics and at high school, I have a magnetic material which is not completely inside the coil. What happens? And we switch the current on. Yes. Exactly. So, by the way, this again is an optimization problem. Just as a remark. So what we do here, we attach some sort of voltage UQ, which drives a current through our coil. This is the simplest form. So this is not very helpful at that point, right? Why? Because if it's inside the coil, then everything stops. So usually what happens, we attach some sort of, of some mechanics to it, which looks like this. You put the string to it, which is somewhere connected, might be at the end of this piston, but also, and usually some sort of damping material. If you think of what I spoke, the damping material is not present because you don't want to have this dissipation, but you're to make our consideration very simple. Well, this system is sometimes called voice coil system. Why? Well, because it operates like a loudspeaker, similar to that voice coil. It's one famous thing which helps to do nano positioning. Now think of, well, here there's some problem because you want to have a friction-free movement. Of course, mechanically speaking, you have usually here some sort of bearing which is attached to that, which can also be resembled by means of this damping. Okay, so as you know, friction is also produced by some sort of bearing, and this company is capable to avoid this kind of bearings, not to use the traditional bearings you have in your bicycle also, and have this friction free. Of course, you know, there are different ways of doing that. The electrical system is that you try to levitate some sort of magnetics. You can put air around this thing, all these things, and they are very, very mature in doing these kind of things. But we want to look at this traditional thing. And with that, you do this positioning, not with just one element. Who knows this Buick platform? Ever heard? A hexapod? Yes? No? I try to depict that. Suppose you have some sort of plate here, and you attach to every position here one drive, and they are also with these. If you move each drive in some direction, you can rotate and push the platform up and down, left and right, forward and backward. So with such a platform, it's called steered platform. With such a platform, you can position. Next time I bring a picture with me, and then you see the right dimension. With such a platform, you operate, for example, driving simulators. These are huge platforms, but here we talk about something which is of that size. With the small voice coil system, for example. It's very, very easy at that point. With that, if you put here on this plate, you remember our photonic example, your fiber, then you can orientate this fiber in any direction and position it in any direction. Obviously, not in free space from here in Karlsruhe and in Stuttgart. This will never work, of course, as we know. But in micrometer or millimeter scales, you have a certain operation range. We want to do the modeling of this system in a very simple way. So Stuart used in
for example, a Stewart platform. It might be something different, for example. So if you're interested, you can look at the company's webpage, then you find something like that. Okay, so what I want to do is right now attach to it first some element knowledge. We know, first of all, we define our position here via one coordinate z. So the coil, the piston is the end position of the piston is defined via z. So this is our mechanical coordinate which we need to use. And of course, we know the electromagnetic material L or the self-inductance of the coil depends on the position of the magnetic material. The more it's inside, the higher the magnetism is, you know. Second, we have a coordinate which belongs to I of t, going here, I of t, because we have to define the electrical system. If you think of the entire thing, then you say, okay, the mechanical part is well defined via Z, because if I know everything how Z behaves, I know all mechanical objects here. It's more difficult in the Stewart platform, so therefore we do not do that. And we have pages of pages of pages of sine, cosine, all these things. It's not funny, but it's not very difficult to do that at that point, but it's more a nightmare in terms of mathematics and positions and triangulation, all these things. Okay, so and of course, you know, if I know the current in the electrical system, I know also everything of the electrical system because with this it is defined. So it makes sense to first. I go on the next page. To define that's always the first step. Please do this in the exams also. Try to find out what kind of coordinates you have and which are independent. Oops, going on here. This is great. Probably there's a fiber optical problem, as you know, or something else. I don't know. Let's see. Perhaps it's working right now. No? Okay. This looks crazy. Because PowerPoint is not operating correctly. Okay, unfortunately, I have to stop here. Okay. I try to avoid to lose everything. But I think it's not possible. Okay, then we stop the task. Okay. Next. Again. Okay. Okay, that's working. So again, sorry for that. Again, our coil, then the piston, and I think I took blue. It might be some sort of mechanical attachment, like the bearing thing. And usually there is a spring or even a damper. We consider the damper. And we also introduce some sort of external source, a voltage source in Q. And with that, we were able to define the variable I of t and the position z. And now next, we define our coordinate system and see what happens. So we have the coordinate 1. My Q E1 is equal to Z, and our second coordinate is the integration of I of t over t, which is the charge. And we define this as our second coordinate, QF1. So as you see, obviously I use here for the electrical part, the flow equivalent. So basically I use some accumulated flow because I'm much more familiar with thinking of electrical systems in currents and voltages instead of using the flux. And for the mechanical parts, I'm happy with the displacement instead of using the impulse. Of course, I can also formulate it with the impulse and flux relation. I talk about this in a second again. So second step, please always do this first. With that, somehow what is independent, what is important, what kind of variables you should think of. This is really important at the very beginning. Okay, then the next is formulate, please. Oops, there's an N too much. Please always first do the Lagrange function, which is given in the mechanical part as being the kinetic energy, which is obviously given by our movement of the piston. And then we have potential energy via the spring, which is given here. And the electrical part is formulated via the co-Lagrangian function, which in our case is a half L of Z I squared, or again in our coordinates Q dot squared. Okay. And the entire Lagrange function is given by the mechanical part plus the electrical part, which is given here. So I glue everything together at, as you say, a half mz squared dot squared plus a half kz squared plus a half L Z Q dot squared. Okay, with that, we can do our calculations. And then if this is done it's routine. It's no transfer knowledge. It's always just apply the things. So you can ask ChatGPT to do the job. Hopefully, I never did it, but yeah, we should test it. Perhaps you can bring the example to me. But at the very end, this is something any Maven program can do for you. So therefore, third step, when I want to do this here by hand, so calculate the Euler-Lagrange equations. So what we have to do is to do the following calculation. For every variable, so we see the right-hand side, which has to be this sources and some sort of damping. And again, I have a problem. That's not true. What's going on here? Strange. So this is working. I think I have a... So sorry for that. Maybe retry. Strange. What I can do is... I think there is a background. This is good, but oh, wow, this is good. Again. I think there's something working. Okay, again. So Fs. Oops. First time. I never had this. No. Again, gone. So if you have an idea what happened, please let me know. Okay, I do not repeat everything here. I hope you have your notes. But I can give you the respective things. Why isn't this there? Okay, so again, the time derivative of L derived with respect to Z dot minus Lagrange derived with respect to Z, and then we have the sources and the dissipative elements, and we know in the mechanical part we don't have any source. Remember the object, there's no mechanical flow going into the system. No external flows in or forces which are pushing against us. So this expression is equal to 0. But no mechanical sources, we can note this perhaps. But dissipation exists due to the bearing, due to the damping element, whatever you like. So I put this here in this position. So there is something dissipated, and it's dissipated in a linear fashion. This is my modeling assumption, and that's it. So with that, the very same applies to the electrical part, but there we have to use the the loop equations, or we can use the loop equations. Sorry. Q dot minus dl dq. And as you know, this again has to be equal to the sources and the dissipative elements. Well, sources are present because we have the voltage source, remember our example, UQ. And now it depends whether you model the coil by means of a resistive element, what I want to do. You have also dissipation, which might be R times I, and that's it. So, and step 4, next slide, if you finish your notes, step 4 is please do the calculations. So evaluate all these equations, put L in, do the calculations, and then you get the expressions, and that's it. And then you have the sort of coupled system. So that's something I want to do now. Or just do the calculations. Which means in our case, so after these 3 dots mean there is some work to do in between, and I leave it out here. So just simple things, what you learned in ODS, just do it. And we end up with and you end up with the following set of equations. We want to interpret them in a second. Q double dot is equal to UQ minus R times I. So obviously, this is equal to I dot. And here again, this is equal to I. And with that, you have your 2 equations. As you see, now we are close to state space form, right? If we think of this part, this is the typical equation of motion, what we know from Newton. But there's a second part which enters into the problem, which comes from the mechanical thing, and it depends basically on the current which flows, not surprising, and the behavior of the coil. And the coil, obviously, now you have to model L of Z, how the coil is constructed, then you get the self-inductance, and you can partially divide it with respect to Z. This is also not a big deal. Remember, just a second. Yeah. And with that, you have this first equation, and then you get on the right-hand side the dz dot.
Second, also not surprising, well, the self-inductance change of the self-inductance times the change of current always gives the voltages. This is something you learned in the first semester of self-inductance. The very difference is here that the self-inductance depends on the position. And with that, you have a coupled mechanical electrical system where the second part depends on the mechanical part, and the first part also on the electrical part, and they influence each other. If you do not respect this, which sometimes happens, if you just look at Newton mechanics and leave everything out, then such nice things which are relevant for today's work have really wrong models, and just thinking of some sort of force here might be difficult. So what you get here is really the specific relation between the mechanical and electrical part. It might be even more complex depending on what is in use, etc., and depends on your physical structure, so basically on the construction of the coil.
Why is Q dot squared the same as Q dot?
No, it's sorry, this is my handwriting. Therefore, it appears the same. Here is it's Q dot squared, it's I squared.
And here it's I dot.
It's always with an I, it's always difficult to represent the dot. Okay. And with that, you have a very simple model of such a voice coil thing. And with that, you can also describe one very important element of the Stewart platform and do the positioning control, for example. And then you have the control engineering things. So please talk to your colleagues, which are all allowed to study photonics or so. Then you can tell them, hey, I'm a control engineer, I'm doing the wiring. So basically, learning these two things together. I think this is fascinating because this is the way how it goes, because I believe, and this is also our experience, in particular, if you have this mechatronical system, if you have these coupled systems of different domains, then this kind of energy approach really helps. And therefore, we use this as the lingua franca for the energy modeling of multi-domain energy systems, so hydraulics, the electrical system, and also the generation system can easily be formulated in such a setting. And we learn in a second to further generalize this, and it helps to give even more difficult settings. And I think I talked about this topic 2 lectures ago, where last year a student was here working for the Hyperloop students group, and they were on the way to produce such sort of first prototype of Hyperloop system. And similar to that, where you do magnetic levitation, and we can do the modeling sort of that, and then do the control for magnetic levitation things. Also nice if you want to do precise positioning with friction-free situations, etc. So therefore, very helpful.
So at the very end, we can say, okay, to glue everything together, we have this energy perspective, this geometric view of how physics behaves. Basically, why geometric? Because we say, okay, there are three moving parts, and we put some geometry, so the holonomic constraints on it. We constrain the entire system not to operate anywhere but on the manifold, so the circle set. And both together give this wonderful formulation. And we get additional insights to it. And there are two questions left. Yes, but with if you remember the flows, the external variables were somehow artificially pushed into the topics at the very beginning. If the first setting of this was invented in physics, they started with conservative systems. No dissipation, nothing, just to describe the movement of the planets. And then you start with that. And so, and this is fascinating, for example, just as a side remark, nothing for us, but if you think of Kepler's equations of describing the trajectories of planets, you remember, okay, he discovered there are Kepler's laws and there are ellipses which are resulting. These are trajectory descriptions, right? Level above is Newton and saying, no, the ellipses stem from the fact that we solve some sort of differential equations. And Euler and Lagrange and Hamilton appeared and said, no, this is even a step above. Your differential equations, Newton, are stemming from an energy principle. And this was formulated. So you have some sort of hierarchical setting. This is how it appears in my head. And then you can ask where, just as a side remark for further interest, is there something, because here we start with something like energy, L. Is there a principle behind the question, what kind of energy I should use? And is there something about, and nothing for us, because it makes it's nothing for control engineers at that point. But it's interesting perhaps for you to know, and you can talk to your colleagues studying physics. Yes, and there is something about, and telling you something about symmetry. So the more, and if you have some sort of symmetry, then some sort of energies might appear, and there quantum mechanics starts to appear. Okay.
So the movement of planets, like it aligns to the average of the potential and
That's one.
does it apply only to the higher project or to every slice of the whole?
To the entire.
To the entire. What happens if you have like multi-body?
Yeah, that's yeah. You have to collect all the stars in the atmosphere or somewhere.
Particularly, let's say I don't have like an entire cycle forward. Where's the start of the point?
No, the point is, it's just a question of formulation. The trajectory starts and ends somewhere, if you want. But if you think of where does the orbit come from, it comes from Newton. And where does Newton come from? It comes from the Hamilton mechanics. Where Hamilton mechanics comes from is from symmetries. So you have this kind of nested structure. Doesn't tell, so this mechanical or this energy formulation just tells you, yes, you can calculate the orbits out of this energy formulation. It's the general principle behind. And why is this so important for control engineers? If you remember, this is also a theoretical hint, perhaps, I don't know. If you think of getting the system in your hand, and if you want to manipulate the system, you're not interested in the specific trajectory, right? At the moment, you have to understand the principle. So whether it's stable or how the entire motion evolves, and not just one motion, all of the possible motions. So, and therefore, we very often start with the differential equations. And then you can say, okay, that's interesting, but if these equations are generated by means of such a principle of physics, so basically energy, can we start with the energy equations directly? And the answer, yes, we can. It's possible, but it's not always necessary because, as you know,
there are easier things we can do, but it's possible to directly start with the Hamilton mechanics, if you want, or Hamilton equations. And that's something I want to add in the next chapter. And is one topic which appeared in the year 2000, around the years 99 to 2010, it was researched for, and therefore it's now topic of this part, where we learned how to do this control engineering with that. Today it's not completely understood, it's still ongoing topic, so we are part of a group doing this research in the world. There are some groups working on that, but it's already much of these topics are understood how to. Not meaning that you can solve every problem. That's not what I want to say.
Okay, so at that point, I want to stop here and want to go to the next chapter. Just for practical convenience, what you do have to do if you want to do control engineering? Well, if you have this kind of multi domain models, you want to achieve multi-domain models, it's important to start with energies, draw down the energies, homodynamic constraints, define the variables, put everything in your machinery of Lagrange differential equations or Hamilton equations, solve them, and find and you get equations of motion. And with these, you can start with every topic we learned in multivariable control and system dynamics and control, nonlinear control, if you like, and others. If you do model-based, traditional model-based engineering, we learned in the second part of this lecture what we can do if we do not have any model because we just have data available. This completely different topic. But if we have knowledge about the physics, yes. And just as a side remark at that point, is that if you can do this modeling, if you know something about the physics, please use it. Because today we have sometimes the situation that everybody says, please use database systems, even in situations where you know everything. This makes no sense at all, because you have to rediscover such nice things like this. And you're much faster in achieving good results using the model knowledge. If you don't have, different. A good combination in some situation might help. So, for example, if you think of this bearing friction system, while describing the friction is always a little bit difficult. So it might be helpful to combine the things. For the classical mechanical part, please use that because it's straightforward. Therefore, describing the friction of such objects in being really precise, think of nanometer scale positioning, or some nanometers, then you have to be really precise, and then friction plays an important role. And describing this kind of friction is really difficult. There are a couple of models to do that, but for the specific object there, database approaches might apply even better. Okay, but now we want to glue everything together because on the one hand, you have now the network perspective of chapter 2 and the perspective of chapter 3 being energy domain. So the question is, there are some advantages for the perspective of having a network, looking at the structure, looking at the interconnection and understanding that. And second, also there's some wonderful things if you think of this energy-based approach. So the question appears really based, I would say, how to combine these because we have advantages from both. And the answer is the next chapter. They are called post-Hamiltonian systems. So Hamiltonian is clear, I think, because here we talk about Hamiltonian system. We have Hamilton, which is in the room, so to say, and we have to deal with them. Why force? So what is the problem with this kind of approach? You might have difficulties to attach, and this wasn't the early formulation of it, because we started with conservative systems. What happens if I have a lot of sources somewhere in the network? Then it becomes difficult to attach this to some sort of some of these equations, and therefore the question here: can we put the fundamental idea of Hamiltonian system like this? So this geometric perspective on the one hand, and this energy-based modeling, can we combine this with the port-based approach? Remember, port, we connect energy transferring, storing elements, and have this kind of interconnected structure which allows for, say, hierarchies, architectures, greater, huge problems. And this has been researched, as I said, almost 20 years ago. It started, and it's still ongoing. It's something where we at the front edge of research, in particular it started in France, in the Netherlands, where a good colleague of mine started the idea to mathematically formalize. He's really a crazy guy with respect to mathematics, doing a formalism. So if you read his books, please are not too much frustrated, because it's really difficult sometimes. So it was to name him, it's Arjen van der Schaft, and also groups in France, which are still present. So they are still working in that area, and some other groups in the world. Here in Germany, and there's a small group at the University of Munich. We are doing a little bit in that direction, and some others in France. But it's basically interesting. It's a European thing, if we think of that. But there are also American groups and Canadian groups. But it appeared here in Europe. Okay, and I want to give you a first impression. So you can teach courses just about port Hamiltonian systems, their beauty and all the things, and how to do control engineering with that, and do it really in a difficult manner, in a light manner, whatever. So it's just a short introduction to give you a first hint towards that direction. Why do I do that? Because we're dealing with this kind of systems in many aspects, in particular for energy systems, because it's a good formulation for energy systems, or a good starting point, better to say, because not everything presses into this formalism. But we start here, as in this lecture on physical modeling, to understand the basic principles about this kind of, well, doing chapter 2 and 3 together to put it, to boil it down a little bit. Okay, let's start. And I started already with the motivation. And well, here again, already in the 50s, this port-based modeling appeared. We know, okay, there's a wonderful way of geometric mechanics, also pretty old, but also you can look at the classical works, 1978, 1999, so, but it appeared even earlier. And last but not least, and this is perhaps the last point,
this was research from a perspective of control engineering. It was not a physical part. The first one, so the network perspective, the first appearance was in electrical networks, obviously, because there, and you still learn in electrical network systems, not on the theoretical side, because it's usually part of the first semester in the bachelor, but yeah, it's part of electrical engineering, right? Almost everything. So I don't know any university in the world which doesn't teach port-based modeling on the electric side. Then not so much, not everybody teaches this port-based modeling for other kinds of systems, or they are not named and that's it. And this is typical physics, okay, but you don't learn it. Usually the physics students learn it in theoretical physics usually. And the control engineering part started with cybernetics in the 30s first, and then later on with Kalman and etc. So it was a control engineering perspective, and the question was why. So first of all, before we go to that, more a theoretical one, can we combine these three perspectives? And the answer, yes, we can do that. This is more on the theoretical side, but there was a, well, say, really disaster situation for dealing with nonlinear systems, because one had a long journey of dealing with nonlinear control theory, starting in the 70s, 80s, and well, main parts of the solution at that time did not work in practice because they were too complicated, and one searched for a different perspective on it. So it was, so if somebody learns perhaps nonlinear control in these lectures, we have here at KIT also. This is from that time, which does not say, I don't want to say it doesn't work at all, but you will learn, Mr. Kubi will always say, well, you have to find something like the Lyapunov function, or you find something, there's a good guess for something. It always starts with that, and this was a little mysterious at that point. It was, and then we have this mathematical branch thing. And that was the point where these groups started to learn a little bit more about this system. So we have these two perspectives: control engineering perspective dealing with nonlinear systems. Basically, linear system theory was quite present. If you remember Kalman activities at that time, that's something we learned about control already. So the basics of it, except all these things, but nonlinear control was quite difficult. And then disappeared. And the second perspective is the modeling perspective. And we treat it first from the modeling perspective, and then at the very end of this part here, chapter 4, I show you some basic ideas how we can use this also for control, and why it's helpful to understand it, why it's helpful to understand such systems in that way. So first of all, I just bring up some or repeat some knowledge you should have from chapter 2, and well, generalize these things a little bit, because at chapter 2, well, we are confronted with a couple of new notations, all these EF stories, and so all these general symbols, and you try to get familiar with it. And here I want to bring up the basic concepts again. And first of all, we start with the following thing. I want to distinguish different elements, different roles in the network perspective first. And if you remember, we talked about storages. I started with that and showed, okay, there are general principles in different domains which apply always. And I talked about resistive elements also, and we talked about some external sources which might influence the system. So perhaps we know this because in the books it's very often called external. So we should talk about sources. If I can write down my notes here. No.
And again, I don't know that an update happened or something else. Really strange. Now it's not so problematic because everything still is still in its new form. Okay, so try again. Okay, so again, perhaps you can note sources here again. And if you remember, we talked about some sort of energy routing. The energy routing elements were the or have been the bonds itself. So how to connect them first, and second, we use some sort of junctions, transform zero junction, one junction, and transformers and gyrators. They do just power routing. Important. And therefore, I want to group them together and take this picture just as a graphical representation of this grouping. I say, okay, I put all the storage elements on one side and collect all the variables governing the storage elements. I take all the resistive elements, and it's like squeezing and shaping a electrical network. Put all the elements on one side and all the others on the other side, and all the rest on which remains, and then the only things which remain open are the routing elements, so the connections. So you get a really strange loop graph at the very end. If you think of a network, if you think of bond graph, well, you can do it by this kind of multi-bonds. Therefore, this double error, where you group all the variables together in one big vector, and then you do the interconnection via the zero junctions, one junctions, etc. This is the in the heart, it's something which routes energy, nothing else, and it's called in this formalism. It's just a notation, the diode structure. And we want to formalize this diode structure. We can think of the system as elements which have an active part or the passive part and dissipative elements for pushing energy into the system and avoiding. No, that's it. And now let's have a look at the different elements first. I just want to highlight this. Energy storing elements might always be represented by means of that the flow is can be represented by means of a negative of one state, and the effort variable can always be represented by the energy function. Remember, H is the general representative of T or U. If you remember your situation, if you do the partial derivative of the energy function with respect to the state variables or some of the accumulated variables, then we get the respective effort variable, right? And I say, well,
and this is something a topic about which we have to talk later, it is sufficient to talk just about the situation that an energy derived with respect to x gives F4 variable. You might say, I remember I had this accumulated flow storages and accumulated effort storages, why only one? And I showed you that's sufficient. No, we can answer this here. Perhaps now, really critical hint in the network chapter. I mentioned something about an element which tries to transform accumulated effort storages into accumulated flow storages. Perhaps you remember that. What is the difference between the accumulated effort and the accumulated flow storages in its pure negative form, do you think? It's just the simple difference. If you look at the formula, it behaves the same, right? If you think of a capacitor and an inductor, you should learn how did you learn the rule for the behavior between the effort and the flow variables of an inductor and a capacitor by heart? I can tell you how I did it. I said an inductor is like a capacitor, but I have to interchange them. Right? That was my rule at the very beginning. So perhaps a little bit too abstract, but it's the very same thing, but I just have to use different symbols. Mathematically, it's the same. What kind of element in bond graph notation or whatever in electrical networks interchanges variables, efforts and flows? There. The gyrator. Remember, it takes effort in and flows out, and flows in and efforts out. If you have a gyrator with a transformation value of 1, you have exactly this interchange of variables, right? And with that, you can transform every. This was my basic principle I learned in one of the first semesters of my studies. As a student, I thought, yes, it's practical. I don't know whether there's a principle, but it works. And here's the same. It works very well. And there's a general principle. You can transform every accumulated effort store in the accumulated flow store by means of a gyrator. So you can look at the inductance, put a gyrator together. So to make it a little bit more explicit, if you have a inductance here, you put a gyrator in between, then you can then this system behaves between these two nodes in a similar way, like a capacitor, and vice versa. So what we can do is we can always transform everything into such a notation where we get the effort out of the energy variable. And this is perhaps appealing. Why we do that, I talk about this later. But it helps, okay? So take the inductances, don't tell the first semester students that it's that easy. Just interchange the variables, that's all. And then we have energy dissipating elements, and these energy dissipating elements might be also linear, as you know, our ohmic law, the linear law of ohmic resistance. Wonderful. And this linearity might help because sometimes if we generally define a relation for an energy dissipating element, it just says, okay, I take the resistance, flow variable, effort variable, and we know that the multiplication of flows and efforts is always smaller or equal to 0. That's the definition of energy goes out, so into heat. And if it's linear, then we can always write a relation which says the flow is calculated out of the default variables. That's a linear relation. That's something which we can bear in mind. And the last one are the external elements which we take as control sources, control flows, or other kinds of interaction points. These are the elements. Nothing new. All the things you have heard of in the chapter 2, but now a little bit grouped together and formalized. So it's really nothing mysterious about this chapter. It's just a different kind of representing the things up to now. Okay. On the other hand, we have all these elements I talked about before, which are somehow routing elements. We have one junctions, the zero junctions, and gyrators and transformers, which are present. So all the gyrators and transformers I have to take, and the zero and one junctions, and there are the various elements with the different definitions. And with that, I want to ask whether you learned this or has ever heard of this wonderful theorem of Telegram. Never? Yes? Somebody nodding? No? At KIT, not? I have to talk to the bachelor degree teachers. It's a wonderful or important knowledge, and it's a theoretical thing. You can't do anything with it. So at that point, therefore, it's sometimes not taught. So no problem if you don't know it. Therefore, here revisited. For some of you, or for others, it's you. But the interesting fact Telegram found out, it's really old, is that if you take a network, an electrical network, you can do this at home. It's a good stop point for today. You take an electrical network and you calculate the power of every branch. You sum it up, but you will find out that it sums to zero. Because some of the currents go in opposite directions, and therefore you get always zero. It's so trivial, and Telegram wrote down this trivial idea. But if you do it, please take a simple network, just a loop or two loops, and then do the calculations, and you will find out, okay, it's summing up to zero. So, and the interesting part is, so for every electrical circuit, we have this. So it's some property of the overall circuit, right? It's some property of the network. This does not apply if you have something which is open. So you have a tree or so. The Telegram theorem does not work. But if you have something like an electrical network properly defined, then you end up with Telegram theorem. And with that, I leave you to lunch. Have a good day. Bye-bye.